For this lesson, we are going to learn about more types of proofs. So last time we learned about the direct proof, and now we're going to learn about other types that are, similar, how they relate to the direct proof and things like that. So just as a review, the statements we want to prove are usually of the form P implies Q. And sometimes it's obvious to see, but sometimes it's a little harder for us to find that P in that statement. And sometimes, P is just like not stated at all. So you might just need to make your P basically like, given everything I know about this subject, if everything I know about the subject is true, then Q. And so, sometimes that makes it a little more complicated in your proof as well, because, then it's harder to know where to start, like what you're going to actually put on line 1 of your proof, because you don't have an obvious P. Because, again, like with our direct proofs, we're just starting with like our first line was P, then we had like our other lines, and then basically we want to get to Q to like prove something. And so when we don't have an obvious P, then it's not always clear what we put on this first line, so we have to do a little more thinking about it. But we'll, so usually you use some kind of like definition or something else that you know about the subject matter. Now, the types of proofs we're going to talk about today are different because they're still going to use the same like P and Q. Like they don't change in the fact that they use this P and Q, but it's not always going to be like starting with P and getting to Q, because you'll learn for certain statements, it's just easier to like kind of move them around and reword them and express them differently, and it makes them easier to prove that way. And so we'll kind of talk about that. But so this is your format of a direct proof, but we'll learn about other types of proof that are not in this format. So the four like core proofs we're going to show are direct proofs, proofs by contradiction, proof by contrapositive, and a proof by counterexample. And so in the last lesson, I already showed you what a direct proof is. To show P implies Q, you start with P and you reason to get to Q. So now let's talk about a proof by contradiction. A proof by contradiction really utilizes this equivalence that P implies Q can also be written as the negation of P and not Q. And so basically the way you format one of these proofs is you start with P and not Q as your line 1, and then you try to get to some type of contradiction. It's often denoted with this kind of symbol. The symbol is called a bottom. It's just, an upside down T or perpendicular lines. It just means that you kind of find something that like contradicts what you're saying. And it'll be easier to see with an example what I mean by this. But basically you want to just show that like, if I start at P and not Q, I get to an impossible state. Something else to note is sometimes like it helps too if you want to just like write your proof a little neater. You can do like P on your first line and not Q on your second line, and that's fine too. And usually instead of saying given, you usually say this is an assumption, because I'm basically saying, okay, let's assume that this is not true, and then like we're gonna show that this causes problems. And so this is usually how you set up a proof by contradiction. So let's go ahead and step through an example. So I want to prove that if x squared is odd, x is odd. So before I do this by contradiction, just try like breaking this into P implies Q and like proving it directly, because it's a pain. So I mean, like so first let's just pull out our P. So our P is x squared is odd, right? And so if x squared is odd, then x is odd. So our Q is x is odd. And so, you can go ahead and try this to prove this directly, but you'll see that it's difficult. It's very difficult to prove it directly. And so this kind of shows the benefit of rewording it and proving it in a different format and showing how that kind of like, is helpful. So you can rewrite it as P and not Q. And I'm going to go ahead and just like write out what not Q is here, so that's easier. So if Q is that X is odd, not Q is going to be that X is even, right? Because if something's not odd, then it's even. So then P and not Q is going to be X squared is odd and X is even. All right, and so I'm going to go ahead and write that up here. X squared is odd, X is even. And then I can go ahead and start my proof by contradiction. So I am going to break it into 2 lines because I think it helps. It helps me. I think it helps me read it a little better too. So I'm going to do just my P here. X squared is odd. And then my not Q here. So X is even. And again, remember, I'm going to do this as assumption. And I'm actually going to start with line 2 with this reasoning about X being even. So I'm going to use that property we had about evens that like, this is one of the common rewrites I told you to remember, where you can write X as 2 times K, where K is an integer. So this can just be even number definition. And so now that I like rewrote X as that, I want to say something about X squared. So that's kind of like a good indicator that's like, maybe I want to modify this so that I can get to like X squared. So let's go ahead and square both sides. So X squared equals 2K squared. And then now that I did that, I kind of just like simplify a little bit. So I can say that like, I can say that like X squared equals 4K squared. And then I actually want to pull this 2 out. So I'm going to say X squared equals 2 times 2K squared. So I'll just write simplification for those 2 lines. And now I kind of have something interesting because like now I have like X squared is 2 times something, which is usually a good indicator that something is even. The only other like rule is, remember, like if I say something's even, like the thing 2 times something, this something needs to be an integer. So I need to be able to claim that like 2K squared is an integer. But like this was something we talked about in the last lesson, like since K, we said here that K is an integer on line 3, then like K squared times 2 is also going to be an integer because integers are closed over multiplication. So if I multiply K by itself and I multiply it by 2, I'm still going to be in the integers. So you can just say that this is integer closure. And you can even like mention line 3, since that's where I say that K is an integer. And now that I have that, now that I have like X squared is 2 times something and that something is an integer, I can say X squared is even. And I can say again, this is just my even number definition. And I'm basically applying that to line 6 and 7. And this is where I get my contradiction. Because I said on line 8 that X squared is even, but on line 1, I said that X squared is odd. So I can say lines 8 and 1 contradict. And so that's how you do a proof by contradiction, is you basically like make 2 statements that are like directly contrasting each other, and then you're like, okay, that's my contradiction that I get. And so, that's one way you can prove something. And this is the same thing as like proving this original P implies Q statement. So even though I like proved it this way, I'm like showing that assuming X squared is odd and that X is even, I get to this negative state. What I'm still proving is if x squared is odd, x is odd. Because I'm basically saying if x squared is odd and x is even, I get a contradiction. So that means that x squared is odd, then x must also be odd. The next type of proof we're going to talk about is a contrapositive. And so again, like, it's just using another logical equivalence to kind of rewrite our P implies Q. So we have original P implies Q, and the equivalence we're going to be using is this, that P implies Q is logically equivalent to not Q implies not P. And so what that means is we can start our proof with not Q and use our reasoning to get down to not P. And since these are logically equivalent, proving this is the same thing as proving P implies Q. So again, like sometimes expressing a problem this way might be easier. So let's go ahead and do an example with this one. And we're actually just going to do the same example. So we're going to say if x squared is odd, x is odd. So again, like our P was x squared is odd. Q was x is odd. And then not P will be x squared is even. And not Q would be x is even. And so now we want to be doing not Q implies not P. So we want to basically start with not Q and get to not P. So maybe I'll write these up here. Not Q, x is even, implies not P, which is x squared is even. And if we can prove this statement, that means we are proving this statement. So that's kind of interesting too, because it's basically saying that these two statements are logically equivalent statements. So saying if x squared is odd, x is logically equivalent to saying if x is even, x squared is even. So that's kind of, an interesting implication of all this. Okay, so let's go ahead and prove this. So again, we're starting at not Q as our line 1. So we can go ahead and write x is even. And for this, you can just write given, because it is given. Like we were given P implies Q and we just modified it to get this not Q. So you can still call that given. So x is even. And then we can go ahead and write x as 2k. So this is all going to be very similar to our last proof, because you'll see contrapositive and contradiction, like those kind of proofs are very common, are very similar, because you are proving the same thing. So and especially like because you still had like this not Q in both of them, so you'll have very similar proofs with contrapositive and contradiction. We rewrote x as 2k where k is in z, and so we just did that as like using our even number definition. And then I can go ahead and square both sides. So x squared equals 2k squared. And then I'm just going to go ahead and do that same simplification I did. So I rewrote x squared as 2 times 2k squared. This is my simplification. And then I'm also going to still use that fact that 2k squared is an integer using integer closure. So all very similar. And now I can use the fact that x squared is 2 times something and that something is an integer to say that x squared is even. And since that's my not P that I was trying to get to, that means I'm done. And so that was just my even number definition. And I could do my square because I started at my not Q and I got to my not P. And so I'm done. My proof, I have proved this statement. If x squared is odd, x is odd. And I've also proven if x is even, x squared is even. So again, like, you know, I said how those two statements are logically equivalent. So this idea is actually like, this version of it is actually called the contrapositive. So like the statement, if x is even, x squared is even, is the contrapositive of if x squared is odd, x is odd. So you might hear that terminology sometimes, like if you've taken a term and you find the contrapositive of it, that's what that means. So the last type of, like, the main types of proof that I was going to talk about was counterexample. And this is really kind of different because you really just use it to like disprove something. And basically the reasoning is like, for a proof, often you're trying to show like something is always true for like in some case, right? Like usually when I'm trying to say like something about x, I'm usually saying it for like all x in the set of integers, you know, if x is odd, then x squared is odd, right? Like it's usually showing it for like all x's in z. So if I can just find one instance that that's not true, then I can just disprove that statement. I can prove the statement is false. And so these are actually a lot more easier because you could just do an example to show like one instance where the statement is not true. So say I asked you to prove the following is false. If x is even, x squared is odd. You just need a counterexample. So take the instance where x equals 2. Well, if x equals 2, x squared is 4, and 4 is not odd. So this contradicts that statement. That proves that the statement is false. So this is just a counterexample. So it's just an instance where that statement is not true. Now, there are some kind of other smaller types of proofs that follow from the types of proofs we've already discussed. And so we will discuss a few of those. So there's biconditional proofs, there's for all proofs, which lead to a pretty important type of proof, which is called exhaustive. And then you have proofs by cases, proof of existence, which is often proven using a constructive proof. So the next type of proof we're going to talk about is the biconditional proof. And so this is something I talked about in our last lesson, but it's basically the idea that like when we're writing proofs, we're basically writing, you know, an implication symbol to get from line to line. But if you're, sometimes you want to prove something like P if and only if Q rather than P implies Q. And so often like we do that with our logical equivalences, which like that is, you know, because like we're really showing like P is equivalent to Q. And so like that's often like the most common biconditional proof we can do. But there are other types of biconditional proofs. And I, you know, if I were, I'm not going to probably have you do any for this course, because it just basically means you have to use stronger rules that like to get from line to line in your proof. Like you have to use rules that actually like, you know, go work in both directions. Like you have to use, you know, if and only ifs, which is fine a lot of the time because often we're using definitions anyway, and definitions kind of like often are defined using an if and only if. But sometimes you can get a little murky. So usually we'll focus more on these like P implies Q, but I still want you to be aware of this type of proof, P if and only if Q. And so this is all just basically what I already said. This is an example of a biconditional proof. I'm not going to go into it now, but we will go over it in the review session. But this is also, I think, just a good example of how you can use your set definitions also in a proof. And so I think that this can be very helpful and kind of show how like we also like use how we use set notation and set definitions and like bring them to logic and back, I think is really like interesting. So This is a type of proof we'll go over in our review session. And again, like another very common one is our logical equivalences. So this is another biconditional proof. And so, you know, like say you wanted to prove that A implies B is equivalent to not B implies not A, then you just make your P A implies B and Q not B implies not A, and then you can either start at P and get to Q, or since this is a biconditional proof, you could also start at Q and get to P, and either way is fine because it works in both directions. And so another thing I want to talk about is another type of proof you might hear of is a for all proof. And so they're just statements that are saying like for all X in S, you know, P of X implies Q of X. And so, you know, basically this just means we're looking at every element in S to show that like if P of X is true, then Q of X is true. So showing that basically P of X implies Q of X holds. And like everything we've learned so far can pretty much be expressed using this for all notation. So like, you know, some examples of what we've seen so far is like for all X and Z, like we've proven, or, you know, like we'll talk about like if X is even, X squared is even, you just basically in front of it put a for all X in the set of integers, this is true. Or you, when we said like, you know, X minus 1 is less than the floor of X, you just say this is true for all X's that are integers. So these are actually for all proofs. I just kind of like skipped this part of the definition. So these are, you know, all can be considered for all proofs. Now this one's kind of interesting. So for like logical equivalences, they are for all proofs, but really like your values, like when you're saying for all, you're saying for all of these all these propositions in my statement, right? So for all A's, B's, and C's, you know, this equivalence holds, and A, B, and C are just either true or false. And so this is kind of why you were able to just use a truth table to prove it, because I can just use like, I can just plug in all possible values of A and B and just like do it that way, right? And just prove it that way. Or sorry, A, B, and C. And so the reason why is because you have this finite set, but I'll talk a little bit more about that in just a second. Another example would be something like, you know, if we have like 3 elements that are integers, if A divides B and B divides C, then A divides C, and this should be true for all A, B, and C that are integers. So this is just showing like, you know, these proofs are all technically for all proofs. But really when a for all proof kind of comes in handy is if you're trying to prove something about it in the exhaustive sense. And so what I mean by that is, you know, again, we're saying like, for all elements in this set, this holds. But, you know, sometimes if it's a finite set, you could just directly look at each item. So like if I have something that's like for all X in Z, like that's not really something where I can't like plug in every integer and like show that P of X implies Q of X like always results in true, right? Like I can't really do that because I can't plug in every possible integer. But like what if I was just saying it for like the values 0 and 1, right? Then I could just plug in P of 0 implies Q of 0 and show that that like gives me true, and then plug in P of 1 implies Q of 1 and show that that gives me true. And that's it, I'm done, I've proved it. Because it only needs to be true for these 2 elements. So this is a proof by exhaustion because, you know, you basically just show it for every element of the set. And so this was often like a common example you did was our truth tables, right? Because you said like for P and Q in the set, because P and Q are either true or false. And then I'm trying to like show like for all P and Q in the set true or false, P implies Q is equivalent to not P or Q, right? And then you just kind of showed that using your truth tables, right? You did your values for P, your values for Q, And then you just show that like this and this will have like the same values, right? And so this is a proof by exhaustion because we're using like all possible values of P and Q in the set. So I'm going to do a more concrete example so that we can get an idea of this, like what it looks like outside of these like propositional logic equivalences. So let's go back to this example we had before where we had like this set of friends F that was Eric, Jose, Nicoletta, and Oksana. And V is Oksana and Eric, and that's the set of the friends who are vegetarian. And N is Oksana, the set of the friends who are vegan. And we basically want to prove that this implication. So if someone is in the set N, then they're in the set V. And I just want to say that this statement holds for all X in F. So this is a good like indicator that I could just, okay, well, there's only 4 elements in F. So instead of doing like some type of high level proof, I just need to show it's for each of these individual items. So I can just kind of like show like, and so, you know, the idea is here is like my P is X is in N. And my Q is X is in V. And so I just want to show that like P implies Q results in like true, right? So that it holds basically for all elements of this statement. Like this statement right here holds for all elements in F so that it evaluates to true is another way to think about it. So you would also kind of think of it as like, it's a tautology like on these values, this statement. And so what I can do is I can just like literally plug in every value. So like for Eric, is X in N. So is he in N? No, that's false. Is he in V? That's true, right? He is in V. So false implies true. That's okay. That false implies true evaluates to true. Jose. Is Jose in N? No, that's false. Is Jose in V? That's false. False implies false, evaluates to true. Remember, like for implication, if your like hypothesis or like the starting part is false, then it doesn't really matter what's here, it evaluates to true. So for Nicoletta, again, like Nicoletta is not in N, so that's false. Nicoletta is not in V, so that's false, so that evaluates to true. And then Oksana. So Oksana is in N, so that's true. And Oksana is in V, so that's true. And so true implies true, evaluates to true. So for all elements, elements in F, we get all values of true. So that's our proof by exhaustion, that this statement here always evaluates to true, it always holds. And so that's an idea of a proof by exhaustion. Like, so it can be really useful when you have these kind of like finite sets. Now, when it comes to like formatting these kinds of slides, or these kinds of proofs, I mean, it's always like, I think the best way to do it is just with a table. Oh, I do have a typo here. This should be, it is true that Eric is in V. But like you can have like a table kind of representation, you know, just like showing like, okay, I checked this was like, this is my P, this is my Q, this is my P implies Q, and then I just show that P implies Q is always true. Like that's always a good way to show it, is just like with a table. If like, you know, you're going to actually do an exhaustive proof, this makes it like easy to read, easy to grade, and give you, you know, full credit on. So another type of, it's basically like a proof by exhaustion, but basically what you do is you break like a set into smaller pieces. And so like one common type of proof by exhaustion you'll see is like some attempt to break up the set of integers. So instead of you're trying to prove something for like x and z, maybe you'll want to say like, I want to prove it for like x even and x odd. And then I basically, like, if I can prove it for all even integers and all odd integers, then it's true for all integers. Another common one you'll see is like, if you're trying to prove it for all integers again, if I'll do like x negative, x equals 0, and x positive. So like, if it's true for all negative integers, if it's true for the integer 0, and it's true for all positive integers, then it's going to be true for all integers. So again, it's just kind of like breaking up your set into sets that like maybe those properties can be kind of helpful. And so I'm going to kind of talk about one of those types of proofs, give you an example of a proof by cases. So an example we can do is when we prove the definition of absolute value. So remember that like absolute value of x is the sine of x, and remember like kind of or signum. So this was basically this function we defined that if x is less than 0, we get -1. If x is 0, we get 0, and if x is greater than 1, we get +1. And so we basically can define the absolute value using that, right? We can say the absolute value of x is just the signum of x times x. And so since like we have this kind of definition here for signum, that's like a pretty good indicator that maybe like for our proof by cases that we can like use that fact. Like we might want to think of the cases of like where x is less than 0 and x equals 0 and x is greater than 0. And so we can do that. So we can break it into cases. So and you can do it whichever order you want, but you basically just have to do like 3 direct proofs now. So you have case 1. Let's start with x as positive, because maybe that's like that one maybe might be like the easiest to kind of wrap our heads around first. And so basically what we want to do is we say x is greater than 0. And what I'll say here is this is my case assertion. So basically I'm just breaking this into I'm asserting that x is going to be greater than 0 here. And then I can say that the signum of x is going to be 1 because it's literally right there in the definition. So you could just say signum definition. And then if I multiply both sides by x, because what I really want to get to is signum x equals signum x times x, so that I can get to absolute value of x. So so if I multiply both sides by x, I have x times signum x equals x. So I just multiplied. And then so let's just like leave that as it is. So we can also do just looking at this fact that x is greater than 0. We can also take the fact that the absolute value of x, like what would that give me back? So the absolute value of x would just give me back x, right? Because x is greater than 0. So basically I can say like I applied the definition of absolute value to line 1 to also tell me that the absolute value of x equals x. And so now I have 2 things that equal x. I have x times signum equals x, and absolute value of x equals x. So now I can just say absolute value of x equals x times signum x, which is what I was trying to prove, right? And so that gives me, so I can just say like plugged line 3 into line 4, something like that. And I can go ahead and move my square over here. But so that's just like, the first part of my proof though, because I did prove it, but I just proved it for my first case. So for x greater than 0. So I have to still prove it for like x less than 0 and x equal to 0 as well. And so, I included in here how you could do it for x equals 0 and x less than 0 as well, just so you have that as a reference point. And the last thing I want to talk about is the idea of the proof of existence. And so sometimes like something you want to show, like maybe I don't want to show that something always holds, but like there's an instance where like something like this holds for at least like one instance. And so, like if we go back to our like example of our friends that are like vegans, maybe I want to say like, there exists a friend that if they're in the set of vegan friends, then they're in the set of vegetarian friends. So I just need to show like one instance where this is true. And so in that case, I just literally say, okay, like we know this is true because we have like x, if we plug in Oksana as our x, then x's n is true because right there. X and v is true because it's defined right here. And then therefore, x and n implies x and v evaluates to true. So we just applied the definition of implication to lines, sorry, this should be lines 2 and 3, not 3 and 4. But this is a basic idea of like a proof by existence, is you basically just take like, you just have to show it holds for like one element if I'm just trying to prove there exists something. The most common like type of proof of existence is going to be like a proof by construction. And so basically what that is you're like building something to show that there exists something that where this is true. So in other words, like for RSA, like we had this kind of idea of like, okay, I want there to be an E and a D so that I can like remember if I say take X and I encrypt it and then I decrypt it. And then I mod it by N, then I should just get back X, right? And so like I want this to be true, but like the only way I can really show that this is true is like by finding an E and a D and then like defining some properties about E and D. And so like I found like an N that's the product of two primes, and then I like chose an E and D that that are equivalent to 1 mod P minus 1 times Q minus 1. And so like I had to kind of like first define N and E and D this way. And then I can like show that like, okay, this is true. And so by this, so this is like the constructive part of my proof, because I actually had to like kind of create these like definitions for N and E and D. I mean, I didn't, but some, very intelligent people did. And, so like that had to be created first to show that this could be true, to show that these things do exist. And so this is often a constructive proof. And I think that like, these things are actually more common than people realize, because often like if we're trying to show something's possible, we have to build something that will do it to show that it's possible to do it. So like, in computer science, it'll often be like, this problem can be solved in this amount of time, and then you have to like construct that algorithm that does it that quickly. Or like this cars can be, like a self-driving car can be as safe as a human driving car. That's shown by like first building a self-driving car and proving that it is as safe as a human driving the car. So like that's the idea of a constructive proof, is you actually have to like build the thing that you're going to be proving something about. And so that's the last type of proof I wanted to talk about. Again, I will not be having you do a constructive proof, but this is something you probably will see in the future, where you have to kind of come up with your own solution to something and then prove that your solution works.